All right. Okay, let's get going. Welcome back to E141, lecture 22. So, couple announcements for today. We will post homework number 9, which is, hooray, your last homework. And that will be due the week after Thanksgiving. And then during that week, we will also post another homework, which you do not have to turn in. We will just basically post a couple problems with solutions that will help you understand memories, because we don't really have time to, because of a project and everything, to go through another homework assignment. And as you have probably noticed, project 2 is up on the class website. And you got some preliminary information in that project. Hopefully you understand the frame of the project and what's it about, what do you need to do in the first week or so, and what it's going to be. We will also provide a lot of information over the weekend, and as you go through the project, we'll put more help pages for you to get going, and you are encouraged to ask questions, as many as you can think of. So here's one. You're going to use the same model as for the homeworks, basically G25.
When you do it through Cadence, can you do it? Does that work? Or will it automatically look for that TMS, whatever it is, model?
Oh, for that one, I guess. Right. So let me confirm that with the TAs. I think that the status is that we are going to use the same strategy as we did in the labs and in the homeworks. And now there may be some discrepancies. For the cadence-related work, you will definitely try to do as much as possible from the cadence environment. And then for the final H-spice verification, you'll do that. But we'll confirm that in more detail over the weekend, because what we are going to do, the strategy is that the TAs will do some rough sketch of the entire project, and they will probably do sort of two extreme cases. They will go with something really simple, for example, ripple carry adder, and just to give you sort of lower bound. This is something you should be really able to do, like yourself, and be able to beat. And just to get a range of where are we really going, they will probably also do another extreme case, which will be dynamic logic, and then say, well, here's really the range of possible answers you may get in terms of your quality metric. And what we are going to do, because we said, well, dynamic logic is indeed really complicated to work with, and it might not work well for everyone in the class. So what we're going to do is we encourage you to use static logic styles like CMOS, pass transistor logic, and so on. And we said if you want to go with dynamic logic, then you get 10% bonus for courage to take on that beast.
But so 10% is power consumption, so you expect dynamic to consume more power. So how do those two?
So that's exactly excellent question. So that's leading me into the next announcements I was going to make. So basically what we're going to do is we are going to separate the curves for dynamic and other people. And so basically dynamic people will be graded on a separate curve, and other people will be graded on another curve. And as I said, dynamic people will get 10 points for courage, provided that they, of course, get good energy times area times speed metric. And last time I talked briefly about the question.
For dynamic people, is there a limit on the clock frequency?
For dynamic people, is there a limit on the clock frequency? That's a really good question. And so what you're going to do for the dynamic people is you actually have to have these like pre-charge and evaluate phases, right? So since your goal is to minimize the speed of your design, then it would be really fair to keep, for example, the clock phase equal to the critical path, maybe a little bit longer, and have a 50% duty cycle. So that in that case, for example, you can't really have really sloppy pull up and then you have really fast like pull down. Pre-charge cannot be really sloppy. That's what I'm trying to um, enforce you to do here. So basically, clock frequency would be critical path plus epsilon, and that's going to be your half of your clock period. Pre-charge evaluate. Make sense?
So like what he asked the question. So even like to get even the delay, we have to make the circuit work.
Absolutely.
So how do we first of all how do we put the clock? Like to estimate the delay, we need the clock.
Right.
So then we can maybe modify the clock. So can you give us a rough idea of the?
Well, a rough idea is the logical effort. It's a very powerful tool, right? You know how many stages you have, you know how much effort each gate carries, and maybe add 30-40% to that for your simulation. And you know that logical effort oftentimes overestimates delay from the experience you had in project one. So you basically work with those numbers, and with a couple of iterations, you will be able to get it to work.
Are we going to have a test bench of all the stuff? Like, for example, the clocking.
You will have, so basically you will use the same test bench as I sketched last time, and we'll put more over that over the weekend to make sure that everyone's consistent. What we're also going to ask you to do is to submit your net lists to us in, we will give you exactly the format what you're going to do. So basically, in order for us to run LVS and functionality checks on your designs, for which we already have scripts, you are going to have your netlists in a sub-circuit format. Your sub-circuit will have to have certain name, and you will have to have certain pinout strategy and naming. For example, you have A 0 through 7, B 0 through 7, carry 0, and then you have Z 0 through 7 and carry out, something like that. And those instructions will be posted in detail. We will also give you, for example, a test vectors that you have to do to apply to your circuit to demonstrate functionality. So you will have, for example, a couple test vectors, let's say 5 test vectors, and then you have to transition from one set of input vectors to another set of input vectors. And what we want you to do in your report, that's also coming up, very detailed explanation, so nobody will be confused. You will have to plot basically one under another diagrams of all your bits at the output. So S0 through S7, we exactly want to see the transitions, and that's also what we are going to run on your design. So last time I gave you roughly idea what we are going to grade, and a lot of people asked, oh, 80%, that's too much for our speed times area product. That's true, but I also mentioned that there will be compressed scaling. That's basically you will get at least 65% if you do everything else right. So let me just clarify a little bit, give you a little bit refined grading policy over here to explain you what's it going to be about. So basically this 80% includes a lot of things. You have to do a lot of groundwork. We will certainly look at all your work and everything that you do. And so what you have to do, basically, you have to do some groundwork to establish your architecture, choose the circuit style. Then you have to do a lot of work in building a schematic hierarchically in Cadence. And then for that, you have a help page on your project website to learn basically how to do hierarchy, which is really going to be handy in this example. Then you have to do critical path analysis. That's going to give you some points. Then you have to do sizing of your critical path. And finally, you have to do functionality check in schematic. Early on, you have to do functionality check to make sure that your design works. And if it doesn't work, this is this X, basically that all the other results that come after that are sort of suspicious, right? And everything falls into water. So no layout points, no. If you decide to basically say, well, this is too complicated for me, I quit at this stage, you can get 30 points max by just basically making a critical path sizing and some design which does who knows what. And you present that grade, so that's still basically the worst case scenario. Now, if you go through the functionality check and you successfully do the layout and you fail LVS, then that's an indication that maybe something wrong with your layout, that you are trying to squeeze in too much area, and then you have to report your propagation delay times area. And again, if you didn't pass your LVS, that means your extracted circuit may have some malfunctionality. So then your results for TP times A have to be discounted a little bit, because now that LVS failed, we no longer have high believability index in your data. And finally, there is this power metric. So basically, you can have two groups, for example, achieve the same area times speed product. Now the question is, which is better? The one that consumes lower power. So that sort of power is an afterthought, but that's something that also has to be considered. And as I said, dynamic and other people will be ranked differently. And what we are going to do is, by sometime mid next week, after we get all these preliminary results from the TAs, we will give you crisp and crystal clear template for your final presentation. We will tell you exactly, like in the first page, we want exactly to see a couple things. We want to see name of your adder topology and the circuit style, and only one bullet, why did you choose that combination in terms of propagation speed, area, and some other parameter. For example, you may say ripple carry adder, standard CMOS. You can say moderate delay, area, low area, and highly regular structure, because I can simply repeat the cells and things like that, something like that. And then you will have to put up a summary of all your results on the first page, and then you have to walk us through your design, critical path analysis, optimization, and we will probably stick some examples from the results that we get over the weekend, so you sort of get an idea into what should be in your report. Any questions?
You said it was a separate curve for dynamic. Is that for both the speed and the power, or just the power?
There is a TP times A, which is the most important metric, right?
Okay.
And the power, right? So dynamic people are compared separately. And this 35 and 10 is basically just the tentative numbers. We don't know yet what is the distribution going to be, but this is the worst case. If you end up being more clustered, then still you will have better scores. So that's basically just the methodology that we are going to look after these things. So primary objective, minimize speed times area. Power is also a good thing to consider, because it shouldn't be totally overlooked. And apparently you have to have your design functional, and basically we are asking for a fair game. Does that sound good? Okay. So stay tuned for more announcements about projects. We graded midterm yesterday. We finished grading, and you did overall really good. This time the mean is around 75%. This is the distribution for undergraduate students. Minimum was 10, maximum was 40. Quite a handful of people got maximum, and the average was 28.7. For graduate students, distribution looks a little bit different, but this makes sense because we really didn't have, this distribution really doesn't mean anything, because we don't have enough, large enough sample to do some statistical significance over here. And so these results are basically also, average was also pretty similar, but the results were sort of more correlated. As one of the TAs noticed, when he looked at these two distributions, he said, well, they are pretty similar, right? Because how they are similar? Because when you look, like, one half of this distribution is similar to the half, so they are about similar, right? The other end, the other tail is not, but yeah, they are still similar, not identical, but similar. Okay, so what I'm going to do today then is, before we go with the lecture, I'm going to walk you through the exam solutions, and then we'll go through the lecture material. Oops, did I bring another blank copy? That'll be good if I didn't. Okay, good. Oops, not good. Okay, so the problem number one was fairly straightforward. I would say this is basically warm-up problem. What you need to do here is to analyze this RC equivalent network and figure out what are the equivalent time constants. So basically what we're asking you to do here is to do Elmore delay analysis. And now applying just the straightforward theory that we developed in class, what you have to do is now you have to calculate your time constants from the source of your network to all the different things, clock 1, clock 2, and clock 3. So now what you need to do is you have to first see the time constant 1. So you look at all capacitances and resistances back upstream. So you have C1, R1, and then you have on this path you have C2, R1 plus R2 plus, then have your C3, only shared resistance is R1, C3, R1 plus, and then you have C4, that's exactly on the path, so you have the sum of these three, C4, R1 plus R2 plus R4, and you also have C5 that has R1 and R2 shared, so that is C5, R1 plus R2. And then for the path number 2, you have basically the same drill. So you have for the C1 you only see R1. For the C2 you see R1 plus R2. For C3 you see only R1. Then C4 sees basically R1 plus R2 because those are on the path. And finally, for the C5, you see R1 plus R2 plus R5. And then finally, for this path, you had this transmission gate, which was nothing but a resistor. And we said that the capacitance was also lumped into this C3. So for this one, you have C1 sees only R1. C2 also sees R1. It is much similar to the example we did in lecture. If you remember that we discussed the situation when you had the side load and then you were only interested to see what's happening at this capacitance, that you had to include all of these. And then you had C3 was R1 plus R3. C4 had only R1. And C5 also only R1. And for this we gave 2 points for each of these, which roughly corresponded to about half a point for each of the terms that you got right. Okay, and then part B assumed that all the R's and C's are equal, and the question was what value of R3 in terms of R is required to balance all these time constants. So you had, when you calculate this, you have that tau 1 is equal to tau 2 is equal to 9 RC, and then you have tau 3 is equal to 5 times RC plus R3C. So you had R3 is equal to 4R. Okay? Then in the second problem, we had a dynamic gate. And so the first question was, is it the best to make Vm of this inverter equal to VDD over 2, greater than VDD over 2, or less than VDD over 2? So there was a range of answers between these two solutions, and what we were really looking after is this, because when Vm is less than VDD over 2, then you have basically faster pull down at the output of this gate. So you have, the reason is faster pull down at output. This will give you 2 points, and this explanation was worth 1 point. So if you, for example, circled this answer and gave correct explanation why you chose this answer, for example, charge sharing, it helps charge sharing, then we still give you 1 point here, because that's correct explanation for your answer, but the answer is really not what we were looking for. And so the part B was, what is the worst case charge sharing scenario? So for the charge sharing, what you want to have is basically you want to have in the pre-discharge phase, you discharge your capacitance to 0, and then what you want to do is to see how much charge contamination you can inject into that node to bring that voltage up from 0 by some delta V. So that is in the evaluation phase. So if this transistor is on in the evaluation phase, that means then you have to figure out what's the maximum amount of intermediate capacitance that you can expose to the output. And in that case, basically the winning combination is that this transistor is off and this transistor is on. Because if transistor A is on and B is on, then you simply have a pull-up. So no charge sharing, right? So in this case, what you want to do is you want to expose this capacitance Cx. And so this is the answer then. A is equal to 1, turns off this transistor, B is equal to 0. And we assume that this capacitance was initially pre-charged, so that you have VDD initially over here that needs to be distributed down here. So now, in order to find what's the worst case voltage at this node from charge sharing effect, what we need to do is to first figure out, oh, this is Y, node Y, sorry. Label this Y, and this is because this is X. So we first need to figure out what are the equivalent capacitances, what are the capacitive contributions for all of these transistors. So let's first start with this node X. So we have that Cx is equal to, so now what do we see here? We see drain to gate and drain to bulk capacitance of this PMOS. And we also see drain to gate and drain to bulk capacitance of this bottom NMOS. So we have basically PMOS is sized 6 times CGD plus C dB, drain to bulk and gate to drain, plus bottom NMOS we have CGD plus CDB, and we also have input capacitance to this buffer, right, to this inverter. So that is another 20 femto. So you end up with 34 femtofarads for this case. Now for the CY, situation is basically very similar. So you have now two transistors that are connected to this node. Both transistors are PMOS. They have two capacitive components. They have drain to bulk and drain to gate. So we have symmetric situation. So we have 2 times 6 times CGD plus CDB. That is equal to 24 femtofarads. Now you notice that there is no Miller effect in this case, because this is now static conditions, right? It's been a long time that your inputs have settled, and now what you're looking into is how long, what's the value of your voltage in the charge sharing mode. And so now you have that your Vx is equal to simply VDD times Cy divided by Cx plus Cy. And since we didn't give you threshold voltage and mentioned that you should really consider this case where you assume that delta V is greater than Vt. And so basically you just balance the charge. Initially the charge was stored on this capacitance Cy, and the amount of charge was proportional to the voltage applied to that node. So it's VDD times Cy, it's equal to Vx times Cx plus y. Cy, and that is equal to 2.5 times 24 by over 58, that is 1.034 volts. And now you see that the assumption was correct, because Vt was probably somewhere around 0.5 volts or so, so delta Vt is indeed greater. So that was set up, and this Vx is 1.034. This was 1 point, this was another point, and this was 2 points. Basically 1 point for transistor capacitances and another point for this input capacitance. So now the next question is, what happens when you have, in addition to your charge sharing, what happens if each transistor further contributes some reverse biased diode current? So what we have in this case is the following equivalent model. So we have this clock transistor, then we have so this transistor is A, and then we have this transistor clock, and then we have the B transistor, and then we have also another clock transistor down here. So what we have at this node is the following situation. So basically now we have this capacitance. So now you have to observe a couple things. So basically first there is a reverse bias diode over here, right, from the NMOS. There is another reverse bias diode from the drain region of this PMOS. So that's sitting over here. And since this transistor is turned on, then these two nodes are connected to each other. So there is another diode from this guy. And since these two nodes are the same potential, then the total capacitance is equal to Cx plus Cy. So now what you need to observe is that assuming that the voltage Vm is equal to VDD over 2, that delta V is equal to VDD over 2 minus the previous value from part B, 1.034, that is 0.216. And now the amount of charge is Cx plus Cy times that delta V, that is equal to this current times the time. And now you know that this current of reverse bias current is equal to two of these come together. So it is 6 plus 6. And also there is this current that's going in a different opposite direction, that is -1, so that is 11. And then when you plug in the numbers, you get t valid is equal to 1.14 nanoseconds. So the grading strategy here was you get 1 point if you write this equation. If you had any propagation error from the previous part B, we did not penalize that. If you basically plug in numbers, get some different value, that's fine. Methodology is what's important. If you figured out this equation, that's another 1 point. And this equation was total 2 points. What we had over here is basically half a point for each of the terms in the equation, and another half point if you got the sign right, because some people also flip the sign for the NMOS because they said there is so many reverse biased diodes, I'm just going to add them all up. And now going to part D, we have to write a Boolean expression that describes this function. So now the strategy over here to develop is basically you either decide if you want to go with the pull-up network or the pull-down network. If you start messing together pull-up and pull-down, you will likely end up with redundant terms if you don't do any Boolean algebra on top of that. So now let's start with the pull-up. So what we can do is basically let's look at what's the chance that we can, what are the combinations of input signals that we can pull up this node out for. So what we observe is basically this is a transmission gate over here. This is another transmission gate and the third transmission gate. So these are the simple observations that we make basically. This is a TG, and this is another, and the third transmission gate. So we analyze this in a block form. So the first transmission gate is turned on when, so out is equal to when B bar is 1, then and if C is equal to 1, then the output is equal to 1 as well. So then I have this another transmission gate which is B, and then this transmission gate is turned on C bar, and it picks up signal A, right? And that's enough, because now you have this pull down guy. If you start messing up with this one, then you may end up with some redundant terms. Everybody clear with that? Okay. You could also basically look under the condition for conditions when your output is equal to 0, and then you are implementing out bar. So you can say out bar is equal to, for example, when this one is turned on, C is equal to 1, then you get 0, right? And then you maybe need to do some Boolean algebra to figure out the expression. But this is basically B bar C plus B C bar A. And this was 2 points. and basically each of these terms was roughly 1 point, and you have negative zero point 0.5 if you add extra terms, or if you have incorrect functionality, then that's 0. So now the question is, how do you implement this gate in complementary CMOS using minimum number of transistors? If you had wrong answer in D, but implemented it correctly in E, full credit. Too bad, right? Because you did what you were asked for. So over here, what you do, that's pretty straightforward over here, basically. So you have, let's do the pull down. So um, we have B or C bar, and then you have A bar, B bar, and C. Then the pull up is fully complementary. So you have, this is B, C bar, and then you have A bar, B bar, and C. So this were 2 points, and if you had redundant transistors, for example, we counted penalized the only ones. So roughly, if you had 1 or 2 redundant transistors in the NMOS, you get half a point off. If you had 3 or 4 or something like that, you had another half point off, so you have 1 instead of 2 points. If you flip your PMOS and NMOS networks, then you have also another then you also have a, was it half? I think it was a half or 1 point off, where you basically say, this is my NMOS, this is my PMOS. That's not good. Some people did that. And that takes care of this logic families problem. So now the logical effort, we gave you first one warm-up example, simple and straightforward, to just figure out if you understand the very concept of logical effort. And so you had to determine logical effort and parasitic delay for these two simple circuits. So what you need to do is then simply balance pull up and pull down resistance to that of a unit inverter. So this is 1, then this is 4, this is 4. So logical effort is, so you know that the inverter is 2 to 1. So this is 3 over here. For the parasitic delay purpose, it's also 3. So logical effort of inputs A and B is 4 over 3. Input C is 1/3. And finally, parasitic delay, you sum up all these capacitances at the output node, divide by what's the capacitance looking back into an inverter. So you end up with 5 over 3 here. This is similar story, just the PMOS, you have 2, 1, 1. So you have 2/3, 1/3, 1/3, and then you have parasitic was 4/3. So the distribution of points, this was 0.5, 0.5, 0.5, 1, 0.5, and 1. And now a little bit more complicated example. I give this example because there was a lot of discussion in the during review session and later on in the office hours in the news group, I think as well. People asked, what if you have additional constraints? What if your input capacitance has to be the same? What do I do then? Do I just, if I have stack of two networks, do I really look only just like at the total design, or I look at on at the block level? And this was actually a chance to do some interesting examples. So what we have to observe over here is a couple things. So first, the problem asks you to figure out the logical effort for this logic gate under the assumption that input capacitances are equal, right? So what you need to observe first is that by inspection of this circuit, you have that M2 is connected to M6, M1 is connected to M5, and this is input C, this is input A. So now since input capacitances have to be equal, that means that A and C are identical. Now that A and C are identical, that means basically that it can easily figure out my pull-down network. So this is basically 1, this is 2, this is 2. Done. So pull down is M1 is equal to 2, M2 is equal to 2, M3 is equal to 1. So now what I need to do is to figure out this PMOS. Now that I know that I have to have balanced inputs also on B, so now I know that I've already lost one transistor to M3. So what I have is now if I label M5 and M6 as X, so this guy has to be X plus 1, right? Let's see, how do we label this? If we do M4 is, so this is X minus 1, this is X, then it's going to work, right? So then simply you need to balance the pull-up resistance to the equivalent inverter. So you have 1 over X plus 1 over X minus 1 is equal to 1/2. When you write the equation, you have X squared minus 5X plus 2 equal to 0. And the only feasible solution is then X is equal to 5 plus square root of 17 divided by 2, which becomes at around 4.5. So you have M4 is 4.5, M5 is 3.5, M6 is 3.5. So each of these were 1 point. So it's all 1 point each, right? 1 point each, and we also looked into some partial credit. So this was, if you observe this, this was 0.5. If you didn't get this, basically, if you get this, we just gave you full credit, no question asked. If you then didn't get that far, but you did some setup, some equations, then you get 0.5 here, then you get 0.5 here, and then if you basically calculate this, then you have the rest of the points. Question?
Why can't you sign up the pull-up network first, and then calculate choose X value for the pull-down network, and then you just use equation something and then solve the size of the pull-down network.
Okay, that's a good question. So the question is, why can't we size the pull-up network first? Because the question is then now, how do you size the pull-up network, right? Because if you say that this is equal to 2, then this is also equal to 2, right? That's not good, because that sort of imbalances your input capacitances. And then for the same pull-down resistance, you may have, actually, you may end up with the sizes of this network such that your pull-up and pull-down are not balanced, right? Because you break this symmetry. So it's easier to figure out pull-down because that's straightforward. That's highly deterministic answer. And then based on that, you figure out the pull-up. Okay? And then finally, the question about arithmetic blocks. This was a carry skip adder. I think a lot of you were really ready to tackle also carry look ahead, but that was kind of late in the lecture, so we didn't want to do that. And so what you had to implement here is basically looking at this block form, you have to recognize the functionality of this adder. Basically understand what this adder does and implement this skip function using transmission gates and inverters. So you have to notice is that this skip function is a simple multiplexer, right? Nothing else. So this skip is this. And then you have this signal P, K to K plus 3, and then you have if that is equal to 1, you take the incoming carry, and then, or if it's equal to 0, then you have the generated carry from this 4-bit block stage where you have all these rippling. So this is simply then in transistor terms, this looks like this. So you have a transmission gate, and so this transmission gate gives you output carry, and if propagate signal is block propagate is equal to 1, this is 1-bit signal, by the way. So that's what we notice. This is 1 bit. So if propagate is equal to propagate condition satisfies, then you have input k minus 3. So that's incoming carry. Or if you don't have propagate condition satisfied, this is P bar, this is also P, then you have ck, which is the carry that is generated. For example, ck here is 7, so you have k is equal to 7 for this block. For example, you have k is equal to 7. You have c7, or you have incoming carry at bit position 4. So this is output carry from the previous stage is the incoming carry for this block. And you finally have this inverter to implement, do the full implementation. So now next question, and this was 2 points. So the way the points go here is if you gave this inverter, then that's 0.5. If you got this structurally correct, that's 1 point. And if you get correct ordering of these inputs, that's another half point, and that's about 2 points. So the next question is, what is the optimal block size B? In this case, B was equal to 4-bit blocks. That will minimize the delay of the adder, assuming that all of these delays are equal, and you can ignore the setup. This was important to observe. So now first you have that your T adder is equal to following. So you have B blocks over here. So that is B times T carry. So you have to generate the carry at the first bit position, propagate through the rest. So you have n over b minus 1 times t skip. Then you come to the last block where you have b minus 1 times t carry plus final sum at the MSB. So now since all of these delays are equal, this is simplified to 2b plus n over b minus 1 times t, and t is equal to all of these little delays. And you have 2 points for this, roughly about half point for each of the terms that you got correct. And then finally what you need to do is to set the derivative to 0. So you have dt add db is equal to 0. So this means that 2 minus n over b squared is equal to 0, and b is equal to square root n over 2, and that is equal to 2 root 2. That's another point for that. And finally, extra credit problems. And I've heard, by the way, that some people had an interview right after the exam or the day after or so, and they got these problems. So that got them quite prepared for that. So extra credit problem was basically meant to help the distribution a little bit. And since this was an extra credit problem, no partial credit here. Sorry. If you got the answer right, full credit. If not, next time maybe. So what we have to do first is to design a 2-input XOR gate using only 2-input NAND gates. So we know that from Boolean algebra that we can use either 2-input NAND or 2-input NOR gates as a function, as a base function to implement any arbitrary Boolean function. And you also were asked not only to implement the XOR gate, but use the fewest number of gates for the XOR. So now if you have NAND gates, here's the solution basically. You have, this is your A and B. Then you have another NAND here, and this is A XOR B. Connect it all up. So to convince yourself this works, so at the output here you have A, B bar, correct? So then you have A, NAND that's the output over here. So output over here is then A, B bar, B bar, and this all goes bar, right? So that's at the output. And then this is equal to A bar B times A plus A bar B times B. So now this is further equal to A bar times A, that is 0. So then you have A times B bar plus, now this is A bar B plus B bar B, that's 0. So this is A XOR B. and you need only 4 gates. So if you did that, 2 points. If you didn't, 0. So the second question was then prove that any logic function can be implemented using full adder cells. So what you needed to do there is basically figure out what is the way I can implement either 2-input NAND or 2-input NOR using full adder cells. If I can implement a base function, I can implement anything, right? So that's the basic idea. So let's first take a look into it is probably useful to take a look at the Boolean table for add function. So we have A, B, C, I, S, and then we have C naught. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1. And then some 1, 0, then 1, 0, 0, 1. Then this is 1, 0, 0, 1, 0, 1, 1, 1. And so this is our full adder. It has inputs A and B, and it has carry in and carry out and sum. So now let's see, how can we somehow, is there a way we can somehow figure out the regularity in this table and figure out if there is any way under, for example, certain carry condition that we can express sum as and or combination of our inputs A and B. So that's the idea. So let's take a look at the situation, for example, where carry out is equal to, carry in is equal to 1. So let's circle all these entries where carry is equal to 1. So we have carry is equal to 1, carry is equal to 1, and over here carry in is equal to 1. So let's see what the sum and carry out bits are in this case. So in this case, you observe that sum bit is equal to who knows what. Carry out bit is equal to, for example, A or B, right? So for this type of is carry out is equal A or B, right? So if you do this, then in the first stage, so you have full adder, so you have A and B, so you have this at VDD, then this is your sum bit, this is your carry out. So you know that at this position you have A plus B. So now another thing you need to do is basically implement an inverter, right? So you know that if you have a full adder, and so this is basically over here, this is a sum, this is carry out. So if I feed in this into the second stage where I have 0 and VDD, what this is going to do is simply invert this output at the sum bit. So I have carry out here, and I have sum, and this is now equal to A nor B. So this now basically implements this function. You can do similar exercise to figure out how to do this with NAND, and that's what we provided in exam solutions. And that's basically also another 3 points or nothing if you did this. Okay. And the way we did this, basically, this was total 40 points. So you have 8, 16, 11, 5. So that was 40. And we also took extra up to 5 to saturate this at 40 if needed. So if you exceed 40, then you are saturated at 40. So this was basically meant to help with people who needed more points. Okay. And we were actually, let me show you something interesting too. So we also looked into your artwork. And here are some of the interesting examples that we scanned in. There were also a few others. We were giving points for this too, by the way. So for so I think we were pretty liberal on grading this. So you get the 1 point or half point depending how good your artwork was. And here are the pictures that were scanned by the TAs last night. And so we had quite a range of ideas. We had a happy end face. We had a interesting illustration of course evaluation over here with some comments. Then this is me dressed up in E141 uniform. This is the status of description of Berkeley EECS. So it's a lot of computers. It's sunny out here, and there is a. What's that? There's happy faces, right? So you have to rectify that. And so basically, there is an adder and multiplier, and there is term over here that basically describes the ratio between female and male population in the Berkeley EX. So that's one idea. There is more transistor people. Here's a transistor face. Here's the layout view with some, I guess, Halloween theme. Or this is 141. You have arms for source and drain, and there is some also transistor representation of really nice font using transistor symbols. And this is also another, here's a sort of cycle of a Friday cycle of one student. Gets up at 9 a.m., goes to Corey, then to 105 lab, then runs to 141 lab, then goes to finish up his homework, and then 1 a.m. goes to Corey, goes back home, and then there was a comment, how sad. Like that's, and couple conventional ideas not necessarily related to class material that were kind of interesting. So you have these online as well. So we gave extra points. So all right. So those that freestyle was actually pretty good, but now let's get to some lecture topics over here. Let's see, where do I have my flip-flops? So what I'm going to do today is we are going to continue with analysis of sequential circuits and carry that forward next week with more elaborate timing analysis. So let me just first recap quickly what we did last time, just to make sure everybody is on the same page. So we analyzed the storage mechanisms in digital circuits, and then we noticed that we have a structure that we call latch that has clock and data inputs, and it has output Q. So this is a positive latch, and the way this works is if you have a clock signal, then you have two modes of operation. You have when clock is equal to 0, this latch is in hold mode, holds previously stored value, and when the clock is 1, then it simply copies incoming data. So now what's really important to understand is that the gate closes at the falling edge of the clock. So the timing parameters that we define for a latch are basically related to this falling edge. So now there is another structure that appears as edge sensitive. And that is basically the situation when we have two back-to-back latches. So this is level, and this is edge over here. So let's assume that we have first negative latch, and that is followed by a positive latch. So this is clock. So this stage is called master. master latch and we have slave latch. So what this does is then, if this is clock phi, then when the master latch is transparent, clock is low, right? So at the rising edge, so here's the last chance for your master latch to copy the data from the input. So at this point, QM is equal to D. After that, your slave latch becomes transparent. But now that happens actually at the edge of this clock, because after this point, so you basically have that Q copies whatever was at the output of the master latch, correct? So slave copies that. And now the point to realize here is that since slave master latch is in the hold mode over here, output of master latch can no longer change. So that means that looking back now one more stage backwards, that means that your data, last chance you can change your data before you capture it at the final output is the hold time before this latch closes. So you have this very narrow sampling window here that actually appears as if you are edge triggered. So that's basically two things that you need to remember. Everybody follow this? Okay, and that's what we are going to do today, to figure out I'll give you some examples how do you implement each of these circuits, and then what I'm going to do is show you some introduction that will be useful for us for timing analysis for next time. So let me go back to slides and show you first implementation of this master-slave register. So when structure is edge triggered, then we call that a register. When it's level triggered, we say that is a latch. So what we have over here is, remember, there were two mechanisms that we can store the state into a latch. There was this mechanism where you can overpower your state, or there is another way when you can basically break the feedback loop, inject the new value, and then close the feedback loop to hold the state. So here is an implementation that is based on overpowering. Basically, the idea here is that if I'm introducing another transmission gate here to break the feedback loop, then the problem is really when I have thousands of these in my real system, and then I have to clock all of them, then I'm effectively sort of doubling the clock frequency. Not necessarily doubling because there is sizing issues, but I'm increasing clock load significantly, and that translates into power consumption. I don't want to do that necessarily. So now the idea is, let's do the overpowering approach, but make sure that this feedback transistor is sized appreciably small, so that when you, for example, want to inject new value at the first stage, you open this transmission gate, and the drive strength of that transmission gate has to be significantly, sufficiently high, such that you can overpower this inverter and achieve the switching threshold of this inverter I1. You will burn some extra power to do this overpowering approach, but that amount of power is going to be less than the clocking power that you would have otherwise if you had to break the loop. So that's basically the trade-off over here. And there is a problem with this scheme in this back path, that you may have basically any disturbance at the output may be actually reflected back all the way through. And there is also ideas in the implementation that people do that, for example, you want to isolate your output, and then the idea is add in a redundant inverter over here, and then take output of that instead of here, so that you basically can downsize this one and then keep all your internal nodes sort of protected, and then drive the large fan-out capacitance with this, right? Because if you have a large fan-out capacitance, you don't necessarily want that to load in the input of this small gate. So that's one of the ideas that's commonly implemented in practice. But now you notice that in order to control this transmission gate, I may need clock and also clock bar. And so far from the timing perspective, I'm assuming that clock and clock bar edges arrive at the perfectly synchronized instances in time. But that's really not the case, because we need to implement this as a buffer. So here's a problem that may occur. So let's take a look into this circuit over here. So what we have is basically also master-slave configuration. And what we do here is a couple things. So first we want to reduce the clock load. And in order to reduce the clock load, we say we implement this pass gate function using only one transistor. We don't really want to do the full transmission gate. That's expensive in terms of power. And we also then implement this approach with breaking the feedback loop, injecting the state, and then keeping it. So what happens over here is, let's first analyze this. So basically we have a master stage over here, and then we have a slave stage. So is this a positive or negative latch over here? So what is the value of clock in which you sample input data? Positive, right? So this is a positive latch. So now what you have here is you have a master-slave configuration. One is positive latch and another is negative latch. So this is positive, this is negative. And therefore, when you cascade positive and negative latch, then you effectively have sampling at the falling edge, because always the edge of the slave latch is what really determines your sampling. So now let's figure out what really happens during this edge of during this sampling edge. So what you can have in this situation is that if we say that this is clock, and then I guess this one is, yeah, the clock and then the clock bar, then you have this overlap period. So basically now you have that your clock bar is high, but your clock is also high. So you are basically now coupling your input all the way to the output when you think that your latch is in the hold mode. And that's the problem. So you have to really make sure that that situation doesn't happen, because what you want is when you get an edge of your signal, that make sure that the previous latch is blocked, that it decouples the incoming data, and that you can only basically copy whatever was stored at node X. So now one way we can get around that is, let me show then. So basically one way we can get around this is that, so if we have a master latch, then we have slave latch, then you can work with non-overlapping clocks. So for example, in this case, if your master clock is equal to this, and then your slave clock is then this, then you sort of avoid the overlap between the two latches. But then you have to pay penalty in time, because there is this time, for example, when you want to sample your slave, then this is really a wasted time. So that's not good, because you're doing nothing here. You're just basically making sure that you have sufficiently wide margin that your data does not contaminate your slave latch at the sampling edge. So there is a number of other solutions. This is basically still the problem, and there is some good circuit topologies that you can use to avoid this problem. Just basically by pure construction of your latch, by good latch design, you can avoid this problem intrinsically. And this is pretty interesting thing to do. Yes?
The clock is showing you don't have the same timing for low and high, so
right, this is just the concept basically. So this means that if you have the two-edge clocking approach, that you have basically master and slave, they have both certain clock, maybe positive, maybe negative. But the idea here is that you want to eliminate this overlap period. This can be also negative, but for the purpose of illustration, I think it's easier to understand this problem, right?
Yeah, I understand that, but so if you want to have some spacing between those edges, you need to have different frequencies.
No, the frequencies is the same, right? This is your clock period T. This is your clock period T.
But it's not evenly distributed. You see the high time and low time.
Right, but it's a different duty cycle then, right? You have pulses. You don't necessarily have to have 50% duty cycle, right? Okay, so let me first analyze a little bit what happens with this clock to output delay of a latch. So basically you have, or a register for that matter. So what we have is the following situation. So basically, let me just illustrate this quickly, and then we will go back to slides to show you. So what we have is data, and then clock, and then Q. So what we want to characterize is how long does it take from output of this clock signal to the output of this latch. And the reason why you really want to do this is, as we will see later on, I'll just draw the big picture here to understand the context in which we talk, is let's assume that this is basically your pipeline stage. You have a clock, and then you have cloud of logic in between, right? So now, in order to determine what is the cycle time for your design, how fast you can clock your design, you ideally want to understand what's the critical path, how much you can squeeze your timing to achieve the highest performance. So what you have over here, you have clock to Q of this design. Then from there, you have logic delay. And by the time before you get the edge of this clock, which is basically the next cycle, right, you have to bring it at least setup time before. So now the question becomes, if your logic delay becomes really large and you're moving your data closer to clock, so this is what happens basically. If your data, if this is data, this is clock, and this is setup time. So what's going to happen if I start moving my data closer to the clock edge? How's my circuit going to behave? And that's what we need to understand next before we can do extensive timing analysis. So shown here are the waveforms of simple edge-triggered design when you have basically data coming in over here. So I'll just put data in red. So this is your data. And so at the edge of this clock, output is basically a copy of your data. So at the edge of this clock, output is a copy of your data. So you're going rising and falling transition. So now let's consider the case where you basically have your data that is coming a little bit closer to the clock. So now in this case, you start basically charging up your master latch. In this case, yes. And if you bring data a little closer, then your latch may fail. And let's now understand what's really going on behind this scenario. So to do that, we need to introduce a little bit more precise setup time. We said setup time is some time that is required for data to be stable before I can capture my incoming data reliably. But then the question is, what really happens? How do I violate that setup time? Is it really like you have data or no data, right? Or there is something that goes on gradually. So this process is really gradual. So you have, if you just look at your waveform, then you have basically gradual degradation of your output as your data gets closer to clock. And this is basically, now we can explain this by looking at the clock to output delay as a function of data to clock offset. So let's take a look at this illustration. So let's assume that our data signal arrives sufficiently long such that I will have no problem catching this at the output over here. And that corresponds to this point indicated in this graph. So I have clock to Q delay. So now let's assume that data comes a little bit closer I'm still far enough from that dangerous setup region. So I still have the same clock to Q delay. And if I bring data even closer, then my clock to Q delay starts to degrade because I'm really now trying to foul up my uh, circuit. When I go even closer, then delay is longer, but I still have correct operation. And at some point in time, you will basically continue this, and eventually you will fail your design. At some point, your delay would say, well, I have now no longer I can capture the data, so I no longer have delay, a valid output. So now the question is, what happens on the hold side? So you also know that you have to hold your data some interval of time after the sampling edge to make sure that you sampled the correct value. If you try to change your mind before your gate closes, your sampling edge is active, then you're also going to have some penalties. So basically the idea here is the same, but just looking from the opposite side. So if you hold your data long enough, then you have certain well-defined clock to Q delay. If you hold it a little bit tighter, so basically you hold it a shorter period of time, then you still have the same clock. And if you keep bringing it closer to the gate, then you have the same effect. So this is, let me show, do I have a slide for that? Huh, I deleted that slide. Okay, so let me illustrate that here. So what you have is this basically situation. So if this is your clock to Q, and this is your data to clock, this is the typical characteristic of your storage element. So now if you plot another parameter that is really interesting from the timing perspective, that is basically sum of your setup time and your clock to Q. That is basically your data to Q of a latch. That's basically what this means is how much cycle time you steal from your logic design, right? Because you have clock to Q, you have logic delay, you have setup time of the next stage. So if you assume that you have the same circuit in the previous and the next stage, it's interesting to look at the sum of clock to Q and setup. So basically setup is defined then by this axis, and if I plot data to Q over here, what I'm going to have is something like this. So what this means is that clock to Q is flat, and then I'm changing my setup. I'm moving closer, closer, closer. And at some point, when I start increasing my clock to Q, now I'm really close, that's good, but then due to clock to Q increase, I'm going to also increase my data to Q. And really high performance designers, what they do is they say, well, now I'm going to give you a really precise definition of my setup time. That is really when I minimize this point, because that's the minimum delay. And that corresponds to, there is a number of ways people do that. If you go from company to company, they have different definitions. So some people do that as, for example, some percentage increase from your clock to Q delay. They say, I can really reliably tolerate 5%, maybe 10% of increase in clock to Q delay, and that's my setup time. If I fail that, that's too bad. Some people say we are really keen on performance, so what we want to do is basically define this as a 45-degree line over here that basically minimizes this data to Q delay. So that's basically the way you can refine. There is a number of definitions. It depends what you want to do. But basically, all you need to do here is understand there is some degradation in clock to Q delay, and there is a number of ways you define setup and hold relative to that. So I guess I will continue with these large structures next time, and now we are going to distribute the exams. Similar strategy as last time. We have